Here we'll be talking about statistical tests. We'll be using statistical tests to eliminate outliers from our data sets, to give us a better idea of the precision of our data set, and also we're going to be using t-tests for comparing data. So the idea behind any statistical test is to confirm or deny the null hypothesis with some confidence. So the null hypothesis is a term that you will see in statistics tutorials or in classes. All the null hypothesis says is that the two things that you're comparing are actually the same thing. They belong to the same data set and not two different data sets. When we say with confidence, we usually attach a significance level to our conclusion. So these two things are the same, and I know that to 95% confidence. I'm 95% confident that these two things are the same. Confidence increases as the number of measurements increases. So if you have three data points that you're using to take an average and a standard deviation, and your partner or another lab team has three data points that they're using, it's going to be harder to prove that those two things are different than if you had, say, 100 data points and 100 data points that you're comparing. So let's look at Grubs' test for outliers first. If you took 4 data points in lab and 3 of them seem pretty close to each other, but the 4th one seems to be an outlier, you can't just throw it out because it'll make your data look better. First, you should check your experimental notes and observations to see if there was an error in your procedure. Did you spill some of the solid onto the bench and have to sweep it back onto your weighing paper? Did you not fill it quite to the line? Was the water that you used tap water instead of deionized water? Any of those things. If there's a reason, right, an experimental reason that this point could be different than the others, then you can discard that outlier. If no record exists for an error for that outlier, then you can perform a Grubs test, a statistical test, to determine if the outlier can be discarded statistically. So the procedure for this is to calculate an experimental g-value using this equation over here, and then compare that experimental value to a value that's in a table somewhere that we would provide for you. And if your experimental g-value is greater than the g-table, then the outlier can be discarded because the two things are statistically different. If the experimental g-value is less than the table value, then the outlier cannot be discarded because they're actually a part of the same data set. So this equation that you would use to do a Grubs test says that your experimental g-value would be equal to the absolute value of the questionable value minus the average value. And in the denominator here we have the standard deviation. The average and the standard deviation is for the entire data set, all 4 points. You can't just choose these 3 in order to do that thing. And then the questionable value either has to be the maximum point, the maximum valued point, or the minimum valued point. It has to be the furthest away from the average. So if these 4 points had these values here, I can calculate an average and I can calculate a standard deviation, and then I can execute Grubs test. I can do the calculating my g experimental value by doing the questionable value, which is the lowest one, minus the average here, and then divided by the standard deviation. I get 1.41. Now I'm going to compare this to a g value from a table based on the number of measurements that I've made. So I've made 4 measurements here, and so my critical value at 95% confidence is 1.463. So my experimental g is less than my table g, so I can't discard this outlier. I have to keep it, and this average and standard deviation would be what I report in my lab report. If you think that you need to discard that outlier, the next step then would be to take another measurement. So if I could take another measurement and it happened to fall near or within my cluster of data, then I could calculate a new average and standard deviation, calculate a new experimental g-value, and compare that to my table value. But now I've got 5 measurements, right? And now my G experimental is greater than my G table value, and so I can discard that outlier. And when I discard that outlier, I can now calculate a new average and standard deviation, and that will be what I report in my lab report. If you do this in any of your lab reports, you should be sure to clearly show the work that you've done to calculate your G experimental and compare it to your G table, so that it is a clear record of what you have discarded and how. Moving on to t-tests for comparison. T-tests are used in order to compare 2 sets of data to each other and determine if they're a part of the same data distribution or not. First, however, you must decide which type of comparison you'd like to make, and there are 3 cases for t-tests. The first case is to compare a set of measurements to a true value. And we've already talked about this in the previous video. We use confidence interval to do that. So you can go back to the previous tutorial about precision and accuracy to review how to do a confidence interval. The second thing is probably the thing that you'll use the most often after a confidence interval, and that is to compare a set of measurements to another set of measurements where both data sets were collected using the same experimental method. So if we're in lab and you and your teammate do 4 measurements and you do a titration of a sample, and the team next to you uses the same experimental method, they use titration to measure the same sample, then this is what you would use to compare whether you got the same answer as your neighbors, okay? So if we could collect an infinite number of measurements, would we find that these 2 data sets, maybe these are your measurements and these are your neighbor's measurements, are actually statistically different, or would they be a part of the same distribution? Because it looks like they overlap significantly, and so maybe you just happen to measure some of the lower points in that distribution and your neighbor happened to measure some of the higher points. So this is the question. Are they the same or are they not the same? Here's a better real-life example. This is data from several years ago in one of my general chemistry classes. I had 2 sections, and this is the distribution of scores from exam 2 that year. You can see that the black class is class 2 and the white class is class 1, and class 1 looks like it has a larger standard deviation, it's a larger distribution. Class 2 is a little narrower and maybe some higher scores. And if you look at the standard deviations, right, who knows if they're similar or not, but the average seems to be about 12 points higher in class 2. If you look at the distributions, they look like they really could be a part of the same distribution. And so the question is, can I just take these 20 students' exam scores and these 20 students' exam scores and average them together because they're actually the same thing? Or do I need to keep them separate because class 2 really did do better than class 1? So there's many steps for this and there's lots of equations, but the next tutorial is going to show you how to do these in Excel, so you won't have to execute these equations by hand. The first thing you need to do is determine if the standard deviations or the variance of the 2 data sets are similar or not. So we do an Ftest. This is another statistical test for comparison, and this is the standard deviation of the larger standard deviation, and this is the standard deviation of the smaller one. So you've got 2 standard deviations, they're squared. The standard deviation squared is equal to the variance, so sometimes you'll see this referred to as the variance. And then once you do a calculated value for f, you compare that to a table value and see if it's true or not. And then if it is true that the 2 standard deviations are similar, then you use this set of equations to calculate your experimental t-value. If your 2 standard deviations are not similar, then you're going to use this equation to determine if the two are a part of the same distribution. And then you're going to compare your experimental t to a table value, just like we did for the Grubs test. If your calculated value or your experimental value is greater than the table value, then they're different. If your experimental value is less than the table value, then they are the same. That is the same rule for every statistical comparison that you would do. So let's walk through this. In Excel, there will be a tutorial for this, but under the Data tab, there's a link called Data Analysis. It'll bring up a menu, and one of the things on that menu is an Ftest. Okay, so that was that first thing. Are the two standard deviations similar or not? You would click on that, complete the options, and it would give you a readout. Okay. This F is your F calculated value, and you would compare that to a value in a table. So here my degrees of freedom are 19 and 19, so I'd have to go across to 19. Here, this table in particular goes from 10 to 20, so I can just look at 20. And I'd have to look at that value to compare and see if I am statistically different or statistically similar. In this case, I did look it up for 19 and 19, and these two standard deviations are statistically similar. So, are the two standard deviations similar or not? Yes. If so, use the equal variance option. So again, same menu from the Data tab, using Data Analysis menu comes up. There are several t-test options. I would choose, because I have equal variance or similar standard deviations, I would choose the t-test with 2 sample, assuming equal variance. If they happened to not be similar, and my Ftest proved that the 2 standard deviations were not similar, then I would use the second option here, which is 2 sample assuming unequal variance. After you set up those options, again, you're going to get a readout here that's going to give you this t statistic or the calculated t value. Okay, that's the number that you're going to compare to in the t table, and the degrees of freedom will be calculated for you here as well. Now, whether you use the equal variance or the unequal variance will change the number of degrees of freedom, so you do need to pay attention to that number as well. Now, this table also goes from 20 to 40, and I have 38 degrees of freedom, but if you look at 95% confidence, I am well above that number there, so these two things would be statistically different. So if we go back to our distribution of data, class 1, class 2, they look like they might be the same, but the averages seem to be significantly different. I did an Ftest and discovered that I have similar variance, so I need to make sure that I use that option in my t-test. And then when I did my t-test, I discovered that my t experimental value is greater than my t table value, and therefore they're statistically different. And all of these tests, the Grubs test, the Ftest, and the t-test, have all been executed here at 95% confidence. So I can be 95% confident that these two classes performed differently on this exam. The third case, which you probably won't be using, at least this semester, would be to compare a set of measurements to a paired set of measurements where each data is collected using a different experimental method. So for example, I have 3 samples, and you are going to use a conductivity measurement to measure the concentration of the analyte in solution, and you get an average and a standard deviation across these 3 samples. Your lab partner, however, is going to collect a visible absorption measurement on the exact same 3 samples. These 2 measurements are very different measurements, but you need to know if these 2 answers, the averages, are statistically similar or not. So this is the set of equations that you would use, where this d bar is the average difference between this paired set of measurements, and SD is the standard deviation of those differences. Basically what that means is I'm going to take the difference between these 2, right, conductivity measurement and visible absorption measurement. Each one of these, I have an average difference and a standard deviation of a difference, and I can calculate t-calc. This is also an option in Excel using that data analysis. This is the t-test paired to sample for means. And again, you get that readout with the t-stat that you would compare to a t-table value.